So welcome everyone. Today's topic we will be discussing is the index design for append-only table. This is a continuation of the topic from last time where we discussed index uh, design for append-optimized table. But today's session is very focused on how indexes are implemented and how indexes work for append-optimized tables. And most of the focus of the talk is more on like the design aspects of it. So there might be like implementation specifics here and there I may have done wrong or may misinterpret. So just those we can figure out from the code how the things are. So I may not have like complete implementation details of all the structures and everything, but the high level idea is to give design overview of how things flow and how things work. So that's the main aspect I will try to cover as much as possible in this session. Okay, so let's get started with what we have. So AO tables. And when I say AO tables, it is a generic statement I'm making, which essentially means this applies both for row orientation and column orientation tables. So when I say just AO or append optimized tables, the concept is applicable to both row orientation and column. If there are very specific column orientation things, I will state that very explicitly that they are only for column orientation. Otherwise, you can take like everything from today's talk applies to both row and column orientation tables. Now, when we talk about indexes, same as upstream and say in Greenplum, there are different index types for tables. So you can have B-tree indexes. You can have bitmap. Then there are like gin, gist. So these are like various index types. What these index types mean is these are the index types, which is like how they are on disk represented. So how they are on disk represented defines their name. So B-tree indexes essentially has like a B-tree structure laid out on disk, and that is what it defines. Bitmap has like bitmaps stored on disk. That is what this index type defines. For append optimized tables, we support all of these index types for an AO table. Now, just keep in mind there is a difference between index type, which is on disk, versus index scan. So what does index scan mean is index scan specifically refers to the execution method or the on the fly way of which how we will be using the index to perform the scanning of the table. So index scan can be different from index type. Just to give a slight example, you can have a B-tree index, but you can have a bitmap scan on top of B-tree index. The bitmap scan is kind of like just in-memory way of doing things. So index type refers to on disk versus index scan is referring to how in memory we are using the things on top of index to do the scanning of the table. So this concept would be helpful later in the discussion where we say index type versus index scan. Those two mean different concepts. Okay, so what we are going to go is we are not going to focus on like any specific index type because index implementation is kind of like transparent to the whole design. Once we take any index type and go through the flow of how AO tables work, the same concept generally applies to other index types as well. So we are not going to see like how B-tree indexes work or bitmap indexes work. We are only going to see how an AO table and index interact between them and how the inserts work and how the scans work for them.
So one quick question, Ashwin.
Mm-hmm.
So is there any special code inside the index access methods to handle AO tables or no?
No.
Awesome. Okay.
And that is the reason where this whole concept of we keeping the TID, CTID format same has helped. So CTID format is effectively same for AO and heap. And that is kind of helping us to not have any logic pushed inside the index methods. Now, I didn't mention this is very Greenplum 7 centric index, which is called Brin index. And for this index type, to answer Deep's question, that does have difference compared to heap and AO. So this index specifically does have uh, if else cases where for AO table the on disk representation is different than heap. But apart from that, most other index types do not do the differentiation between table types. Okay, so that was the initial part. Now I'll just bring in what all players are there going to be in today's talk, go through those players to understand, and then we can go through the whole flow. So first and foremost, we have our relation file. So this is relation file essentially is for the base AO table. So when we call it file means this is like going to be the on disk file for the AO relation. Now, as we had discussed before writing to the file, we have stuff in memory. So this would be our area where we would play with, like, consider this is our var block, which is the in-memory block where the AO table block would be constructed in memory first before it goes and gets written to the disk. So these are the two starting players. The other players which come in when we bring in indexes is, which we hinted last time, but we didn't go in detail, is there is table called block directory. So this is a auxiliary AO table, and we'll see how this table gets used today. Then there is another table called GP underscore fast sequence. So if you don't have indexes, life is very easy. But with indexes, all these other players start coming in play and makes the things little complicated. So this is GP fast sequence, which is also a heap table. Block directory is also a heap table. And then the last player we will have effectively is the actual index. So these are the players which will be involved when we are talking about indexes for AO table. So when we go through the flow of how the insert work and how the scans work, each player's functionality and each player's role will become clear in the system. So let's say we have a insert statement coming in. And the first insert statement effectively does insert 3 odd numbers in the system. So I'm taking a very small scale example. So effectively it inserts 1, 3, 5. So those are the 3 rows it wants to insert to the AO table. So the way the flow works, and this will provide importance of like why everything is done in this way is when we get the row 1 to be inserted, the logic for AO insert is that for every row to be inserted, we need a CTID as we talked, because the indexing mechanism uses CTID to figure out or to do the fetching of the rows from the index. So the way the indexing works is anything you write to the index, final end result would be it will give you a CTID, which is called the identifier or the tuple identifier. So for indexing purposes, we need to generate tuple identifier for each tuple we insert to the AO table. So as soon as the insert statement starts, the first thing it says is I need a tuple identifier for these rows to be inserted. Now the mechanism used for getting the tuple identifiers for AO table is GP fast sequence table. So insert comes in and insert says give me the batch of rows. You could have done one by one, but that would be inefficient. So we say, give me a batch of row numbers, which I can use to insert rows to this table. And currently that batch size is like hard coded in code. The batch size is 100. So first time you come in, it says, give me the batch of row numbers. So it says, I'm giving you a batch of 100 row numbers. So you have from 1 to 100 row numbers, go and use them as you wish. So what happens is then in memory, we will start putting these blocks in. So we will essentially write 1, 3, 5 in this block. And what we will say is this has a row number of 0, 1. Here 0 effectively represents segment file, and this represents the number which we got from fast sequence, which effectively is represented as the row number. So that's the like CTID is for all other system, but within AO code, this is also referred to as AO tuple ID. So AO tuple ID has this format of AO sec file and AO row number. That is how CTID field is split across. So what will happen is this gets the CTID as 0, 1. The next one will get 0, 2, and this will get 0, 3. So these are the row numbers which this will get. Now, when we are doing the insert, what happens is every insert which we do, every tuple which we insert gets written here. But the way the executor works is when it says exec insert, it gives that exec insert to the table A. We will put a 1 here, and I went ahead a little. I can come back and say, so we will do an insert here to the table, and then the executor itself calls and puts this entry into the index. So for index, it will say the index column is same as the column which we are inserting. So it will say it has a key as 1 and the CTID field is 0, 1. So that's kind of the index entry which we will make for it. So see here that the entry in the index has made to the disk, like this page can get flushed to the disk also. So index entry is made much before this entry is even landing to the AO table. That is one of the differences AO has compared to heap. In case of heap tables, the actual page entry always exists before the index entry is made, but that's not the case in case of AO tables. So next entries we will make is 0, 2, we will have 3, and 0, 3, this has 5. So this effectively fills up the block. These entries make to the index as well. And then once this block becomes full, what we effectively do is we go ahead and write this block to the physical file once it is full. So when we write this block to the physical file, we know which offset we are writing. So right now the offset which we are writing is 0. So this block lands in the file here. And once it lands to the file, what we do is we create an entry for this block which we have written to the file in block directory. So block directory, what does we write? Block directory writes which segment file we have written the block to. What was the first row number? So this block effectively says my first row number was 1 for the block. So it says what is the block number and what is the row count in the block. So in this case, we inserted like 3 rows. So it will say my row count is 3. So block directory says the row number, the first, what is the first row number used by the block. So in this case, the segment number will be 0. It will say the first row number used in the block is 1. And the offset we are writing this block is at 0th offset in the file. And it also says how many blocks are, how many rows this block contains. So it effectively will say like there are 3 rows in this block. So what effectively the block directory gives you? Block directory gives you very quick way to figure out what this block contains, how many rows, and where exactly in the file this block is. So that happens for the first block directory entry will get created that way. Now the next insert comes in. And let's say the next insert we get are for 3 even numbers. So effectively we are inserting 2, 4, and 6. So this block we have already written to the disk. So no more need for this block in memory. Now the next insert comes in. The first thing it will do is go to the fast sequence and says, give me the next set of rows or row numbers which I can generate. Now here you can see that in previous we asked for 100, but we only used 3 row numbers. But given the way fast sequence is implemented, there's no way for us to reuse the row numbers again. So the next set of row numbers are going to start from 101. So effectively 97 row numbers in this case got wasted. But that's how the implementation is. So next time we asked, the next insert comes in, it asks, we overwrite and we say, I am giving you a next batch of row numbers. So effectively row numbers starting from 101 to 200. You have those row numbers which you can use for the next batch of insert. So what it effectively does is effectively does the same thing. It starts to create a block in memory, starting with this will have the 0 and then the row number would be 101. Now, when you write this entry to the index, in index, what will happen is because let's say this is a B tree index, B tree index will keep the data sorted order based on the key. So in index, it will come out that entry would come here and you will get 0, 101 inserted in the index. And this process keeps going where effectively you will have 4 and 6 inserted. And you would have 0, 103. And index would have the similar entries where you will have 4 and 0, 102. And you will have 6, 0, 103 insert. So that is how index will look like. This is how the block would get created in memory. And then finally, when we will go ahead and write this block down to the disk, block directory entry will get created corresponding to this, which effectively will say the same similar thing, where it will say it will just sec file 0. The first row number for this block is starting at 101. The offset at which this block is starting, let's say, is let's say 1000 for simplicity here. So it will say the offset starts at 1000, and this block also has 3 rows in it. So that's how the on-disk representation for block directory would look like. And then this block will like no more exist in memory because it has made to the disk. So that's high level flow of how index inserts work with AO tables. Are there any questions from the perspective of like insertion pattern for? Okay, so I'll move forward and explain like how the scan would work, because this was the insert part. But if we get a query, let's say this part is visible as well. So let's say we get a query which says select from this table all the tuples, give me which are less than 5. So if you have to use satisfy this query using index scan, what will happen is first thing we will go and do is pick up the index and say scan through the index, apply this clause and figure out which rows from the AO table need to be returned to the user. So it would scan through the index and it will figure out like all the rows less than 5 needs to be returned. So which all these rows will qualify for the results. Now, if we have done like normal index scan, the way index scan is done for heap tables, then that question would get answered why it becomes inefficient for AO tables. So let's say index gives us all these rows to be returned. Index is going to say go and fetch row 0, 1 from the table and return it back. The flow is you get the CTID, which is 0, 1. You effectively will go to the block directory and see where exactly this 0, 1 block is on disk, because we don't know where that block is. So how we use this information? We use 0, 1. 0 effectively tells us which segment file. And then when 1 tells us when you're scanning this, where exactly that row is present, because based on first row number and row count, you can figure out if this row number is lying in between which block. So that is where block directory helps us during scanning of the indexes, that it allows us to convert from row number to the actual physical block where the block is in the file. So this will say it maps to entry 0 and that block is at offset 0. So we can effectively using this go and read block 0 from the file to get the row corresponding to this one. So let's say that's what we do. It gives us 0 offset. For AO table, what we will have to do, let's say this is AO table plus a compressed table. So we will have to read this block in memory. We will have to uncompress this block in memory. And after uncompressing this block, we will get effectively 1, 3, and 5 rows. And then we will say to user that, yes, it wants a row 1. So return this row 1 to the user from the block. So that is how first row will be fetched. Now, if we are going in the index order or index scan, it will say next row is 0, 101. We will do the same mechanics, figure out which block this maps to. It comes in here, it will say it maps to second block. Its offset is 1000. So we will come to file. We have to read this second block from the disk, uncompress the second block, and return the row. So this whole in-memory thing will go away, gets replaced with the second block contents, which are 2, 4, 6, and we'll return from it row 2. Then we hit the third row. If we are scanning in this order, that's where the problem becomes, that we are duplicating this. Like for scanning third block, if you scan the block directory, it will finally give you again that it maps to the same first block. We'll go here, we'll realize that you will be fluctuating between block 0 and block 2, reading the block, uncompressing it, returning one row, then reading the next block, uncompressing it and returning second row. And you will keep like round robbing between these two blocks. And that becomes super inefficient to do index scans for these tables. And that is the reason for AO tables, irrespective of the index type on disk, we always do bitmap scans. So the scanning which we do for indexes for AO table is always bitmap scans as of now in the code. And the reason for that is that what we do is, instead of doing this piggyback of like just scanning in index order and flipping between these blocks and rereading the blocks, to avoid all that, we create a bitmap. So we don't go to the table at all. We don't go to the block directory at all. We scan the index and we create a bitmap first of based on row numbers of which rows needs to be returned to the user. So it's a very lightweight bitmap which says I want to return row 1, row 1, 1, 2, 3 from the first block, and then I want to return row 101, 102, and 103 from the second block. So this bitmap is created after scanning the index. And then what this bitmap helps you is, bitmaps helps you to serialize the IO. So even if index is randomizing, using bitmap, we try to serialize even index scans for AO table. So we create this in between bitmap, and then we use this bitmap finally to perform these lookups. So we say, once you have created a bitmap, take this one row, go to the segment, figure out the block directory entry, and read the block. And we keep using this automatically, the logic, the way it works, it will keep returning the rows from the first block which satisfy the condition. And as soon as we hit 101, we know there is no reason to come back to block 0 because we have already returned all the rows which might be needed by index from block 0. So the reads to the actual file for AO table still remains sequential even if we are doing index scan. So that was the main design point why bitmap scan is always preferred for AO tables compared to doing index scan or index order scans. Now, yes, agree. There are cases where this aspect of creating a bitmap becomes inefficient. And those cases are like, if you're doing the full index scan and you're scanning the whole table, this is much efficient. But if you say this query had, again, this is not good example, but let's say this query was returning 1 million rows. But if the query had limit clause to it and it said, I only care about like 10 tuples. So if it is a case of like you are using index scan, but you're saying the output or limiting the output, in that case, creating this bitmap itself by scanning the full index first becomes an overhead, because to create a bitmap, you will still scan the full index, create the bitmap, and finally you will use this bitmap only to return 10 rows instead of 1 million rows. And that is where it becomes inefficient to do bitmap scan. And for those cases, just doing a regular index scan would have been helpful, because even if it was inefficient, you would have done like 5 scans and then stopped instead of like reading the full index, creating the bitmap, which is going to be a waste of time. So that's where this part of like, should we do index scans or not for AO table versus should we always fall back to bitmap scan is a question, and there is PR open to enable index scans, but we need to do all those costing to see when exactly it would be efficient to pick up a index scan versus doing a bitmap scan for the tables. So that was the high level flow from this, like how the scanning works and why we have bitmap in picture and what are the components come in play for the things. So are there questions around these areas?
Ashwin, I have a quick question. Yeah, we know that in the first sequence, the row numbers are not sequential, as you said. So my question is, if if that for the case we wasted 19 numbers after the first three numbers,
Right.
right? Yeah. So in the bitmap scan, is there any space for the wasted numbers, or it just compacted?
So that's a good question. And at least what I am familiar with is I am more familiar with bitmap indexes, like the on-disk representation. And at least bitmap indexes definitely have a logic to have compression, that if all are zeros, like there are many, many zeros for large extent of rows, then it is able to represent that in a very compact fashion. I'm not very, very familiar with the bitmap scans, bitmap structure being used, but I'm confident that it would also have compression and logic enabled, because there are cases even for heap tables where bitmap scans are used, and I am hoping it has logic for like having compressions and large series of ones or large series of zeros represented in a much efficient fashion.
Okay, so um, just uh, be curious. If we can make the row numbers sequential, for example, when we use the first three numbers, we tell the first sequence to start from 4, but not 101. So if we can do that by some way, can we make the bitmap more efficient?
Uh, it's possible bitmap might be more efficient. I'm not very 100% confident that serializing the full rows will help it make it efficient or not. Because when you're performing index scan, in general, the bitmap can have large holes because you can have like one row matching the condition, and then you can have like many rows which don't match the condition for the index. So even if we efficiently allocated rows to allocated sequentially the rows based on how the keys of the index are, we can't guarantee how the bitmap would get created.
Okay,
Because
okay, I understood.
yeah, so that is the reason this data structure inherently irrespective needs a efficient implementation, which I believe it should be having, because we can't control how far apart the index rows TID would be coming out.
Okay, okay, I understood. That might be not matter much. Okay, thank you.
Correct. Yeah.
Quick question, Ashwin. So you said that the var block is going to be kind of thrashed if we go in index order, right? So first of all, we will look at the first var block, then we'll load the second var block, then we'll again go back to the first. So isn't there enough memory for more than one var block in memory?
No, not, I don't think so. So you can consider var blocks very similar, like Currently, we talked about only row tables, right? As soon as you
Right.
bring in columnar tables, there is one var block per column. So let's say even if you're scanning like 100 columns, you will have 100 var blocks already in memory, which is too much. And then if you're scanning like 10 AO tables at the same time in the system, already you have like that many blocks in memory. So because this is not controlled similar to how shared buffers are controlled, this is all processed local memory. So across the system, if you have like many AO tables being scanned concurrently, that's just the memory usage will keep increasing.
Mm-hmm. Gotcha.
And here we just explained about like 2 blocks, but this pattern can repeat for like n blocks. We don't know.
Right. Mm-hmm.
Okay. Are there any questions? Because I plan to have this focused session very short and only focused on indexes. So I'm fine to take more questions and hope here, but I have like no further topics to present than what we have already done.
I don't see any questions on chat. Does anybody else have any questions?
I have a question. When we do like insert, if we haven't filled the var block in memory, do we always flush the
We will,
block to disk?
so there will be 2 cases where we flush. So one is if the block is full, then we flush and write it. Otherwise, if we have exhausted, so if we have done with all the thing. So if this block's capacity is like 3 rows, but user only inserted 2. So if the statement is done, then also we will just complete whatever it is, we will write that many rows, or if it is full, then we will write that many rows in the block. So those are the 2 conditions in which we will flush to the disk. And we write to the disk. Flushing happens when the statement is fully complete. So not for every block we flush, every block gets written to the memory, like written to the OS cache. And then the flush happens finally when this insert statement ends, when we call like flush and close the file. So at the end of the statement is where finally the flushing of all the blocks happen.
So if we always like insert just one row, would we have a lot of holes?
We not exactly holes, but we have a lot of overhead, because for every row, this will have a block header, because every block has a header. So you'll have one row and block header. So it will kind of become very similar to a heap tuple, where each tuple has a header in it, but it would make the whole flow very, very bad, because each block has like an entry in block directory. So just one row, one block, this whole metadata will get blown away too much for AO tables. If you're having like, if you're using indexes and all, and then you're doing like singleton inserts or updates to AO table.
I see. Thanks.
Yeah, so it works, but that is where we say like AO tables are more designed for like bulk batch inserts and batch modifications, for because all the design is from that perspective. It can support, and there are customers who use AO tables for singleton updates and deletes, but it's not efficient use of the system.
There
And
will definitely be a lot of bloat
correct.
in the block directory table and everything.
Yeah, and even in the fast sequence, right? Like
Yep.
you allocate a batch of 100 and you're using only one. So it's like all 99 rows are going waste and waste and waste.
We have never tried to kind of optimize the fast sequence stuff, right? Because I imagine like we are choosing a number 100 because we don't know how many rows we're going to insert.
Correct.
I maybe that piece of information is encoded somewhere. Like, I don't know. For example, if you're doing copy, maybe you can get that information from the size of a copy buffer or something like that.
Correct. It's still tricky, but there are cases, and I'm extremely happy with the PR Howlin opened because that is trying to achieve, like it at least showcases that fluctuating number of fast sequence is definitely helping the performance part. Because 100%, like fast sequence is a heap table, so doing an update to fast sequence, you need to do a lookup, you need to do a wall entry for it. So even wall generation adds the traffic. Plus every heap in place update currently also triggers doing cache invalidations. So a lot of work is being done at every 100 row number iteration. So if you're doing much bigger row size insert, uh, I do feel there is scope for optimization. It just we need to play with numbers and figure out what would be the actual way to do it. Like in case of CETAs you're doing, or in case of like maybe backup and restore cases, we may have idea of like what the row count is of the source table, which can act as guidance, I believe, in some cases for us.
Right.
The slight nuance I didn't mention is this existence of block directory currently is completely, and as it's clear, its existence only is helpful if you have indexes. So if you don't have an index, maintaining and keeping this around is of like complete waste, because you're just going to do always sequential scan and you're never going to use it. And that's the reason currently it's optimized that this block directory is created on first index creation on a AO table. So when you create the first index on AO table, this block directory gets created. If you never create an index on an AO table, the block directory is not even created at all. So that's kind of one of the good things as of now in the code.
Okay. Ashwin, I have a question.
Yeah.
Yeah, you just mentioned it will the benefit for using bitmap scan is help the I/O serializable I/O, right? It make the like a sequence scan for the target AO table. So as I know, bitmap scan also comparing with index scan is also some sort of serializable I/O. Because it may looks like may help make the heap scan like a sequence scan. Is that right? Yeah. As I understand. So comparing between this, because bitmap scan using prefetch to help to improve the something like a sequence scan to improve the I/O
Right.
IO speed. So how about if we can apply the prefetch or something similar like async IO for a append-optimized table, because it may be
Correct. Yeah, I think 100% we should look into, even just for sequential scans also. I believe that is the avenue which has been not explored, which we should do to add more prefetching logic. Currently, we rely a lot on the operating system. So like we rely that there would be prefetching enabled and prefetch size enabled at the operating system level when customers are running Greenplum, and that is what we leverage for AO tables. But I think we knowing more from the code, we should not just rely on the operating system, but try to provide as many hints and as much things from our side to it.
Okay. So is there any significant concern or something you have about for prefetch or async read to AO table?
No, I think prefetch we should definitely do. Async
Okay.
IO part we need to again evaluate and see. Given how Postgres, it's helping Postgres, and Postgres is trying to implement async IO.
Yeah.
I'm confident it would help Greenplum as well.
Okay. 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 Thank you.
I have a simple question. Where are the block directory and the bitmap stored? Are they stay in memory or disk?
So block directory is a heap table. So block directory is on disk. So this is this all information. I didn't explain like exact format. There's a format for like there is a tuple which gets created, and that tuple effectively has like mini pages implemented to write all this information in like this is not like every row in block directory. There is like these are rows within mini page, and then there is one tuple created which has like n mini page entries for it, but block directory is on disk. This bitmap, this is in memory. This is created on the fly. When we are running the query, we figure out what index entries match to the clause, and then this part is created in memory, but the block directory exists on disk.
Okay. Where are the index in the picture at the stay?
This has its own file. So if you create a b-tree index, b-tree index effectively gets its own, like I'm calling it rel file because that's kind of how you will see it in the PG class, but it's effectively a file on disk. And this representation, how we write will depend on what type of index it is. So b-tree will write this in like b-tree form, bitmap will write this in bitmap, gist engine, and brain indexes. Each index types have their own representation, but this makes again to the disk.
Okay, thank you.
This was really awesome and very detailed.